You are falling towards a black hole, not watching it from safety, not seeing it through a telescope, falling into it. Behind you, the universe is still alive with stars, clocks, voices, and light. Ahead of you is a darkness so complete that even light cannot climb back out. But the strangest part is not that you will die. The strangest part is that, at first, you might feel nothing. No impact. No wall. No warning from nature. If the black hole is supermassive, millions of times heavier than the sun, its event horizon can be so enormous that you may cross the most dangerous border in the universe without noticing the exact moment it happens. To someone watching far away, your fall becomes impossible. Your clock slows, your movements fade into slow motion. The light from your spacecraft stretches redder and weaker until you disappear from view. But from your side of reality, you do not freeze. You continue falling. That contradiction is what Albert Einstein's universe allows. Two observers, two different stories, both true. Because a black hole is not just a giant object with powerful gravity, it is a place where space-time itself has bent so deeply that the future points inward. Once you cross the event horizon, escape is no longer difficult. It is no longer a possible direction. So the real question is not simply whether you would survive. The real question is what you would see, feel, and experience as the universe behind you speeds up. Your final light fades from everyone else's sky, and every road ahead leads deeper into the dark. This is what happens when you fall into a black hole. For this journey, imagine the black hole is not small. A stellar mass black hole, formed from a collapsed massive star, could destroy you before the most famous part of the journey even began. The gravitational pull on your feet could be much stronger than the pull on your head, stretching you apart before you reached the horizon. So we choose a giant, a supermassive black hole, like the monsters hidden in the centers of galaxies. It may contain millions or billions of times the mass of the sun, yet its event horizon is so wide that the tidal difference at the boundary can be gentle. That does not make it safe. It only gives you enough time to understand what is happening. Your spacecraft is still outside the horizon, but the sky has already changed. The black hole itself gives off no light from inside its boundary, yet the space around it may be brilliant. If gas and dust orbit nearby, they can form a blazing accretion disk, a flattened whirlpool of matter heated by friction, pressure, and violent motion. The center is dark, but the edge can glow hotter than stars. If this disk is thick and active, radiation could kill you long before gravity finishes the job. X-rays and high-energy particles could tear through shielding. A real black hole is not a clean doorway in space. It can be surrounded by some of the most hostile environments in the cosmos, but imagine your approach avoids the worst of that fire. The black hole is quiet enough for the thought experiment to continue. You look through the window, and the universe no longer looks straight. Light from stars behind the black hole bends around it before reaching you. A galaxy that should be hidden behind the darkness appears smeared into a curved arc. The same star may appear twice, its light taking different curved paths around the black hole. You are seeing Einstein's gravity with your own eyes. Before Einstein, gravity was described as a force. The sun pulled Earth. Earth pulled the moon. Every mass attracted every other mass across space. But Einstein changed the picture. Gravity, he said, is not simply a pull. Mass and energy curve space-time, and objects move through that curved space-time along the straightest paths available. Near Earth, the curve is mild. Near a black hole, the curve becomes extreme. You are not falling towards a surface. You are moving through a geometry that is closing around you. As you descend, your own clock still seems normal. Your breathing continues. The lights in the cabin flicker at their usual rhythm. A pen floating beside you drifts as if you were weightless. If the spacecraft is freely falling, you do not feel gravity the way you feel weight on Earth. For a small region around you, the fall can feel almost peaceful. That peace is the trap. Einstein's equivalence principle hides inside this part of the journey. It says that free fall can locally feel like floating in empty space. Gravity has not vanished. Instead, you and everything around you are following curved paths together. You feel weightless because nothing is holding you up against the fall. But the wider universe tells another story. The black hole is changing how light reaches you. Stars ahead of you may appear compressed into bright, distorted patterns. Stars behind you may seem to gather into strange shapes as their light is bent by the curved space-time around the hole. The view is not a normal sky anymore. It is a map of paths light was barely able to take before it reached your eyes. If the black hole is spinning, as real black holes almost certainly are, the journey becomes even less ordinary. A rotating black hole drags space-time around with it. This effect is called frame dragging. Outside the event horizon is a region called the ergosphere, where space itself is being pulled into rotation so strongly that nothing can remain still relative to the distant stars. You may fire your engines to resist the spin, but the geometry keeps sweeping you around. The black hole is not only pulling inward, it is twisting the surrounding space-time like a cosmic whirlpool. You are not just falling down, you are being carried around as the dark center grows larger, but someone far away sees a different universe. They watch your spacecraft approach the event horizon. To them, your clock appears to slow. A flashing beacon on your ship blinks more and more slowly. Your signals take longer to climb away from the black hole's gravity. The light loses energy as it escapes, stretching into redder wavelengths. You grow dimmer. They do not see you cross the horizon in a clean, dramatic moment, but you also do not remain there as a visible frozen statue forever. That is a common misunderstanding. In practice, the light from you becomes so delayed, red-shifted and faint, that you quickly disappear from observation. From outside, you fade at the edge. From inside your own experience, the edge has not arrived yet. There is another common myth about this fall. People often imagine that as you approach the horizon, you would watch the entire future of the universe flash before your eyes. The real answer is more careful. If you were somehow hovering very close to the horizon and then escaped, far more time could pass for the outside universe than for you. That is gravitational time dilation. But hovering there would require impossible amounts of acceleration as you approach the boundary, and you are not hovering. You are freely falling. During the fall, outside light can be bent, shifted, and compressed into strange patterns. Some signals may appear sped up or distorted depending on your path, but you do not get a clean movie of all cosmic history. You receive only the light that can still reach your world line before your own future ends deeper inside. Einstein's theory does not give you a magical view of eternity. It gives you something colder. Every observer gets only the information that space-time allows them to receive. In other words, the black hole does not just distort what you see, it limits what seeing can ever mean. From here on, even sight itself becomes a prisoner of geometry and fate. You look forward. The dark circle has grown until it dominates the sky. Around it, light forms strange rings and warped shapes. The black hole is acting like a gravitational lens, bending paths that normally would never meet your eyes. It is not only matter that falls here. Direction itself seems to lose its ordinary meaning. Near the black hole is a region called the photon sphere. It is not the horizon, and it is not a safe place to hover, but it marks where gravity is strong enough for light to travel around the black hole on unstable paths. A tiny disturbance sends that light either outward or inward. If you could survive and look around from near that region, the view would be almost impossible. Light from behind you could curve around and appear ahead. The universe would seem folded around the dark, and still, your own body may feel little. That is the most unsettling part. The view tells you that reality is being distorted. Your senses inside the cabin may tell you that nothing urgent has happened. Then you reach the event horizon. This is the boundary everyone fears, but it is not a wall. There is no metal shell, no burning surface, no line painted across space. The event horizon is the last boundary from which light can escape to the outside universe. It is defined not by what you feel, but by what signals can still reach others. If the black hole is large enough, you cross. No flash, no impact, no scream from space-time, just a quiet passing from one kind of future into another. A moment earlier, escape was still possible in principle. A powerful enough rocket, fired early enough, could still have carried you away. A moment later, no engine in the universe can return you to the outside. Not because the black hole pulls harder than your rocket can push, but because the direction called out no longer leads out. Inside the horizon, every future-directed path leads deeper. This is the key to the horror. On Earth, escape is a matter of speed. Throw something gently, and it falls back. Launch it fast enough, and it leaves the planet. But inside a black hole, even the fastest possible signal cannot travel outward to freedom. Light itself is trapped, not by a material barrier, but by the shape of space-time. You turn the spacecraft around. You fire the engines. The ship shakes. Fuel burns. The instruments respond. But all you have done is choose a different inward path. In Einstein's geometry, escape is no longer a destination. Behind you, the outside universe may still send light inward. Signals can fall after you. You may still receive pieces of the world you left behind, warped and shifted by gravity. But nothing you send can climb back out. A final message, a final image, a final scream of radio waves all remain inside. The universe can still speak to you. You can no longer answer. Now the journey becomes physical in a harsher way. At the horizon of this supermassive black hole, the tidal forces may have been mild. But as you fall deeper, that mercy fades. Gravity changes with distance, and the difference across your spacecraft begins to grow. The nose of the ship, closer to the center, follows a slightly different path than the tail. Metal begins to strain. The frame groans, seals bend, instruments flicker and fail. The black hole is not crushing you from all sides like a press. It is stretching one direction and squeezing another. Your body becomes part of the same geometry. If your feet point inward, they feel a stronger gravitational effect than your head. The difference grows from uncomfortable to fatal. You stretch lengthwise, sideways, you compress. The process has a strange name, spaghettification. The name sounds ridiculous. The reality is not. It is what happens when gravity stops acting like a gentle pull and becomes a gradient across your body. No material strength can resist it forever. Bones, organs, cells, atoms, all are forced into paths that separate. For a smaller black hole, this might have happened before the horizon. For the giant black hole, it happens after crossing, hidden forever from the outside universe. Ahead lies the singularity, according to the simplest version of Einstein's general relativity. But here the script of science changes tone. We can say what the equations predict. We cannot honestly say we know what nature truly does at the deepest center. The equations say space-time curvature grows without limit. They point towards a singularity, a place where density and curvature become infinite in the mathematical description. But infinities in physics usually mean our theory has reached its boundary. General relativity is extraordinarily successful, but it is not a complete theory of quantum gravity. At the center of a black hole, space-time may require quantum rules we do not yet fully understand. The singularity may not be a literal point of infinite density. It may be a signpost telling us that Einstein's theory, powerful as it is, cannot finish the story alone. That is why your fall is more than a dramatic death. It is a journey to the edge of known physics. Einstein's theory explains the horizon. It explains why light bends, why time differs for observers, why the distant watcher sees you fade, and why you feel nothing special at the crossing. It explains why escape becomes impossible after the horizon. But as you approach the deepest interior, the theory begins to lose its voice. The horizon acts like a cosmic curtain, preventing the outside universe from seeing what happens where our equations begin to fail. From far away, no one sees your final destruction. There is no last image of the singularity, no photograph of the center, no broadcast from the deep. The last light from your ship has already stretched into invisibility. Your story has not merely ended, it has become unreachable. This is perhaps the most disturbing difference between dying in ordinary space and falling into a black hole. In ordinary space, signals can spread, evidence can escape, light can carry news. Inside a black hole, the news has nowhere to go. Einstein did not create this as a horror story. He wanted to understand gravity. He wanted to replace Newton's invisible force with a deeper structure. But once gravity became the geometry of space-time, that geometry revealed something far stranger than a force. It revealed that the universe can contain regions where the future itself is sealed. A black hole is not simply a place where gravity is strong. It is a place where the map of possible futures has been rewritten. Return now to the beginning of the fall. You are moving towards darkness. Behind you, the universe races ahead. To a distant observer, your clock slows, your light reddens, and your image disappears. But you do not remain frozen at the edge. You cross. For a moment, perhaps, nothing feels different. Then the curvature grows, the ship fails, your body stretches, and somewhere ahead, beyond the reach of every outside observer, Einstein's equations point towards a place they cannot fully describe. That is the terrifying lesson of falling into a black hole. It does not merely trap light, it traps every possible road back. What feels more disturbing to you? Crossing the event horizon without noticing, or knowing the outside universe will never receive your final story? Subscribe to explore more documentaries through Einstein's questions, the questions that still lead us to the edge of reality.